Hello, Hemant. Hello, Haley.
Hi.
Nice seeing you connected. Let me make you co-hosts. Okay. And it will take maybe just a very quick to bring on slides. Yeah, many thanks for submitting your works in time. I understand how hard it is under pressure of other courses, so it is much appreciated that you made these efforts. Okay. Oh, hello, Payman. Thank you for connecting. So your co-host, you can admit others as well. Anand is also connecting. Let me make Anand a co-host as well. Hello, Anand. Yeah, thank you for connecting and enabling camera. Okay. So if you see anyone trying to join, please admit immediately. We do not have any secrets or restrictions. Well, happy holidays if you're celebrating something right now. I'm not asking how did you spend your weekend, because after giving you an assignment of completing this long writing, it will be not the right thing for me to ask. But many thanks for your dedicated effort to complete write-ups. And as you can see, the printing company, the publisher, accepts corrections. So I'm looking over all materials and may write something, but if you see any errors that you want to fix until tomorrow morning, you're welcome. You can compare your work with works with others and get some inspiration from there. And I look forward to see your slides tomorrow night and to hear your presentations on Wednesday evening, after which we will be done with this class. So I will complete the part of the academic lecturing today and tomorrow. So the lectures are not connected to anything in our projects. We just need to finish some methods. But after completing the lectures, I would like to stay here and answer questions, if any. And if you're speaking, I do not hear. Probably your microphone is.
Yeah, can you hear me?
Yes, now I can.
Okay.
Okay, good. So in this computational chemistry course, we were combining the knowledge of theory with practical skills, and then doing projects that can be compared to experiment or to calculations by other methods. And there is a method of time-dependent density functional theory, which is, it is not the whole story of that. We didn't have time to cover all methods in computational chemistry, but it is like a necessary minimum that may help us to survive in the world and do independent research with computational component. So tomorrow I plan to show as a last practical lecture, I plan to show a flow chart of density functional theory, which will have similarity to geometry optimization, to Hartree-Fock self-consistency, to the DFT self-consistent, and there will be similar idea, similar procedure for tdft. Today, I'm going to show some practical aspects of running tdft calculations, and in the audience, I know that not all of class attendees can join anytime, but today we do have Haley connected. So Haley is professionally running tdft calculations. So if I tell something wrong, she's the best expert to correct me. Or if you want to learn more than I will be telling today, please ask Haley, and I have no doubts in her professionalism in running and interpreting tdft. Haley, are you volunteering to answer questions or correct mistakes of the instructor?
I'll do my best.
Thank you so much. It's much appreciated. So what is the context? So last time when we had the lecture, we were overviewing a procedure, how the computation of transition densities is converted into observables, and observables are oscillator strengths. So just as a brief summary, tdft method is a tool that predicts transition energies and oscillator strengths that allow us to compute spectra. Today, I will have minimum of theories and formulas. I will just basically, in the ideal world, today's lecture should be a lab, but we did swap the academic review and the lab because we needed to bring everyone into one room at once. So I will briefly show what is the input of the tdft calculation, what is the output, how to generate spectra, and how to interpret the content of the output file in relation to what we did on the previous lecture. So so here is a brief summary. The tdft theory gives us transition frequencies or transition energies if we put a little h bar here. The transition densities do depend on frequencies or on the number of eigenstate. And by applying so-called procedure of trace of product of two matrices, transition density and matrix of transition dipole, one is getting expectation values of transition dipole. So bold symbol symbolize that it is a vector, capital I that it is labeled according to each individual transition. And as soon as we know the transition dipole, we can take it absolute value square, multiply by constants, and get oscillator strengths. The equation below is must have single index here. What? I need to bring just a second. Yes, should have the single index here, single index here, single index here. Here we have h bar, and then it will be equals to delta E sub I. So the absorption spectrum is our goal. The frequencies and transition densities is what comes from computation. And here is the little procedure for interpreting the results of calculations. So the practical example will be based on the titanium hydroxide, a model, and it will be done in the Gaussian software. Recent improvements of the WASP software also allow.
Dr. Kalim,
Yes?
you're not sharing your slides anymore.
I don't? Thank you, Haley. I would like to share slides. Is it better now?
Yes.
Okay, yeah, thank you. So the example will be based on the titanium hydroxide that we did consider at the beginning of the course when we were looking for basic electronic structure. So it's titanium 4+ and OH- group. So total it is neutral. It is so the total charge of the system is 0, and the multiplicity is singlet 1. So in Gaussian input charge 0, multiplicity 1. And in order to speed up calculations, I just checked it an hour before the lecture to rerun this calculation anew. So I was doing it in the same directory where I used to have the output from DFT calculation. So there is a way to import the check file from DFT calculation and use it towards computing tdft. It is not necessary, but it shortens time. It makes calculation quicker. Okay, so practical example of tdft calculation. I need to admit, I do not run tdft every day, so probably Haley is doing it much more frequently and gets more experience. So in the Photon directory, there is a template for input for the header of the tdft calculation. Right now, if you're doing more modern calculations, right now there is an available Gaussian 16, which has a little bit more bells and whistles, but basic configurations, basic input and basic outputs are the same. So when we were doing only DFT, we were using this key. So functional and the basis set. Here at the bottom, we have charge and multiplicity. In case we do tdft, there is a keyword td, which is time dependent. And then there are 2 additional keywords, which tells how many excited states we do want. Yeah, this one can be replaced by something else. And there are a few additional keywords which one can keep or remove depending on the necessity. For our practical things, I need only this one. So here is the file that I just checked to be running 60 minutes before coming to the class. So here I'm requesting time-dependent calculation for singlets for 27 states. And here is the geometry of the titanium hydroxide. At the very beginning, I did request to use the same check file which was used for DFT. No, it was not HF. It was DFT calculation for titanium hydroxide that we used at the beginning of the class. And upon preparing this input file, .com file, I was just typing G09 space and then this input file name here. It took maybe less than 10 minutes to complete, a little longer than tdft. And upon completion, it does generate the file as it is usual, this name of the file, .log, which contains all input data, which contains this transition energies and oscillator strengths. So first, I would like to show how to practically process these recordings and how to generate spectra. And later on, we will look once again inside this file and see how to interpret its content. So in the binary directory, yeah, here is the directory where example was done. So if you want to repeat and make sure it works, you can copy paste all files, or you can try to apply tdft to your own model. There is a Perl script in the binary directory that takes the log file and extracts the transition energies and oscillator strengths into the file that has the same name and same format as the output when we were doing our VASP calculation. So OS_strengths. So if we, it is done just to unify the research procedures. So if you look inside this oscillator strengths file, the column number 3 contains the value of oscillator strengths, column number 4 contains transition energies. And titanium hydroxide is known to be white transparent material. So the lowest transition is in the UV range, which makes sense. There are 3 projections of transition dipole just in case it is needed for any calculations. So there is another script that does convert oscillator strengths into spectrum. So this script is located here. If you want to use it on other machines, not on the Photon, there is a same name, genspector gauss.f, so you can just copy paste it, transfer it to different machine and recompile. So after launching, so this file is just reading oscillator strengths and generating spectrum. Same as we do in VASP, after you launch it, makes a dialogue with the user. So it asks how many transitions, what's the energy range, how many steps, line width, and then it generates a file where it uses additional part of the file name to tell what was the width. So next step, same as we did before in our VASP exercises, we do want to look inside this spectrum file and identify the and convert it into graphical form. So the first line contains wavelengths in nanometers. The second one contains transition energy in electron volts, and the other 3 contain absorption spectrum as a continuous data with different normalization procedures. So I was copying this file into more standard spectrum and then using the same scripts which we were using in WASP. So GNU plot space GNU prog SPE1. So this GNU plot script does generate a file spe1.ps, which we can convert into PDF, and then one can download it in local computer and see that this spectrum has structure of individual lines because the transitions are very sparse. Right now, I'm not performing a comparison, but generally, it would be really interesting and useful if you do a practical research to compute spectrum based on independent orbital approximation as we do in WASP, to do this tdft calculation with correlated electron hole, overlay it and see how they relate to each other. Do they have common trends? Do they have discrepancies? And by such comparison, one can learn a lot. The same spectrum can be plotted as a function of nanometers. Then the UV range starts at about 350. So here is visible, and here is the UV. So this material belongs to UV range. Okay, let me quickly check if this little instruction makes sense, or if there are any questions on this material. So everyone is it okay? Yeah, thank you, Anand. Thank you, Haley. Thank you, Hanman. Payman, will you be able to run it if needed? Or let me formulate differently. Please give a signal if there are any questions or if you've been not able to run it. Okay, no signal means acceptance. Haley, did you found any errors, any glowing errors that you want to correct, or it was okay?
I think it was okay.
Okay, yeah, thank you. Okay, so now I am done with practical instructions. So if our course will be a little longer, now we would just make an exercise so that everyone tries to run this calculation. I will walk along seats and check if you are able to do it, but we are skipping it for the sake of time. Next little section of today's meeting, I will invite you to look inside this dotlog file that stems out of the tdft and analyze the records there. So in order to get these records, I need to open dotlog file and scroll, browse through. Here I use slide from like previous years, different runs. So the transitions energies can be slightly different. What I've got today was 3.7, maybe because there were different procedures of optimization involved. But general structure is the same. So if one looks through the dotlog file, there one identifies about 75% of the file from the beginning. This records excited state 1, excited state 2, and as many excited state as you requested. Basically, when we were recently overviewing how to create images, how to create oscillator strengths file, it takes dotlog file and parses. It looks for lines with excited state and extracts transition energy and oscillator strengths from there. So what else is contained? What else is contained in these records? So it does contain the orbitals which contribute to the lowest transition. So for titanium hydroxide with 1/2DZ, this orbital number 24 is HOMO, 25 is LUMO. So the lowest transition is contributed by electron promotion from orbital 24 to 25, from HOMO to LUMO. There are additional pairs of orbitals contributing to this transition, but they are less intense. This list includes only the most important ones. So it's, well, if you take absolute value square of this thing, it will be percentage of this transition to overall transition. So there is transition energy in electron volts, transition wavelengths in nanometers, and oscillator strength. And here it shows a pair of orbitals that contributes to this transition at most. If you look for excited state 2, which is expected to have a little higher energy, you see that it is composed on different transitions. So HOMO -1 to LUMO, and from HOMO to LUMO +1. Remember, at the end of last lecture in Tuesday, we were comparing two images, the orbital picture and excited state picture. So the excited state picture includes several orbital transitions. How do these things relate to our knowledge, our ideas about the transition density? So last week, we were looking on example, on symbolic representation of transition density with pairs of orbitals. So here is the overall density matrix, and the portion in the box is transition density matrix. So the element HOMO to LUMO is exactly what is shown here. So in some sense, this excited state distribution does show us element by element transition density matrix. So this would be row 1 for excited state number 1. Let me check if this interpretation makes sense, and let's vote. Are you okay with this interpretation? Thank you, Anand. Thank you, Hanmant. Thank you, Haley. Payman, just tell or show if you disagree. Okay, no disagreement. Let's continue. So let's make the same analysis for the next transition. So here we do have density matrix for transition number 2. And we do see that it doesn't include, it has 0 or almost 0 in the HOMO-LUMO element, but it has non-zero element in HOMO -1 to LUMO. So it will be this one. And it has non-zero element in HOMO -1 to LUMO +1. So basically, since the overall density matrix, transition density matrix is too big, it just for human analysis, it demonstrates the most glowing, most significant contributions. So we can get an idea of how transition density matrix look like for the given excitation. So as many excited states, as many transition density matrices are computed. And records in the dotlog file just show most significant elements. If one wants to analyze overall density matrix, there are specific keywords in the input that will save each of these density matrices in a separate file and allow to analyze them. Okay. So the values of all elements of density matrix were helpful, were used to compute the main observable, the value of the oscillator strengths. So for each transition, Gaussian software does job for us and finds most important observable for us, the oscillator strengths. And this is the information that we are using. Okay, and here is an example of making the spectrum. So when we looked at the spectrum a few slides ago, it was computed in a different time with different widths of individual line. So it was more like individual peaks. Here, I believe I was using quite big width parameters, therefore they overlay and form continuous line, but the procedure was the same. Okay, so basically, I'm done with plan for today. So practical steps for running tdft calculations, interpreting, converting the tdft calculation into spectra, and analyzing the dotlog file, connecting it to the tdft theory. The next portion of material will be related to the meeting of tomorrow, and there will be a little overlap. So I will just start because we are ahead of time, and then since we have different audience on Mondays and Tuesdays, there will be some overlap. So the tdft theory, its foundation and theorems were developed in the community by several researchers, including Hardy Gross from Germany, and it was like effort in the community. But the final form of the tdft that is being solved by software was offered by Professor Mark Casida from Canada. So here is his web page, which I was visiting like about 10 years ago. And here is one of the ways how the equations of tdft are typically represented in the community. So Haley, I believe you were attending Friday group meeting where August was presenting a paper by Tretiak and Mukamel. Is it right?
I was not there.
Oh, okay. Then I am not under danger to repeat the same thing twice. So on Friday meetings, there was an attempt to overview a part of the paper in the back on the lower line, and the paper itself on slightly different subject. It just mentions tdft as one of the building blocks, but here. And we were discussing it on the previous week. So here I'm just repeating the definitions of which equation we were solving. So the theorems are originally formulated for time-dependent Kohn-Sham equation, where instead of eigenstates, instead of orbitals, there is a wave function that does depend on time. If one electron orbital is dependent on time, then it is connected. It originates from time-dependent potential, which typically comes from external electromagnetic field, or by same as in the spirit of DFT. If orbitals are time dependent, it means you can reconstruct how the potential was depending on time. But both the wave function, potential, and density are converted from time domain to frequency domain by Fourier transform. And in the Fourier transform picture, one is looking for change in the total density as function of position and function of frequency, because for electromagnetic radiation of different frequencies, we have different changes, different response of the density. And this change is formulated in the following nomenclature. So we have occupied and unoccupied static orbitals with an expansion coefficient, which is a density metric. So here is we have density, and here we have density matrix. Density matrix. This density matrix elements are typically denoted by uppercase X and Y in the tdft community. And in order to find eigenfrequencies and eigen states of this X and Y, one is solving eigenvalue problem. So supermatrix acting on a supervector, where the A and B coefficients include Coulomb interaction between electrons and hole, and if this interaction is absent, it is just orbital energy subtraction. And in the language of tdft, these k factors are derivative of the potential over density, or second derivative of the total energy over density. So second functional derivative. Okay, I believe this should be enough for today. Let me check if there are any slides. Yeah, there are some more slides, but it will be too much for today. It's better if we just absorb the information that was delivered. So please let me know if the information from the class is okay. Let's please vote and tell if you're okay or you have some concerns and questions. Thank you, Haley. Thank you, Anand. Thank you, Hanmant. Payment, just tell if you disagree with something. Okay, so it looks like everyone accepted. So I suggest we are finishing a little earlier today. If you need to go, if you're busy with anything, please feel free to disconnect and depart. If you have any questions about class material or about your projects or presentations, feel free to stay and discuss. I will be staying here just to answer questions, if any.
Thank you. Yeah, thank you.
I have a question about what we discussed earlier, if you don't mind.
Oh yeah, sure, absolutely.
Can I share my screen?
Yes, I believe so.
Okay. Is this more of what you were looking for? Did I do this correctly?
Yes. For panel A, it looks like you are showing on the occupied orbitals. Can you show for panel A both occupied and unoccupied?
Oh, okay. Yeah, I can fix that.
Okay.
That makes sense. I was confused.
And for panel B, did you fix the oxidation state? Is it like 3+ or 2+?
2, yes.
Okay. Yeah, it makes sense. It makes sense.
Okay.
And
so can you see my cursor?
Yes. And for panel C, it is also overall 2+, right?
Yes.
Okay. Yep. Makes sense.
So it's affecting like this area of the density of states, correct?
Well, when I was looking on your orbitals, on the orbitals of your combined model, I noticed that either HOMO -1 is localized on oxygen.
Yes.
So it means it will be like, it may trap, hole, and decrease, lower the absorption or emission, which is not a problem. It's just a observation of real system. And I really like that the part of the HOMO that it is on oxygen shows this 4 spheres, like 2 pi orbitals, right?
Yeah.
Yeah, it's interesting, and it is reasonable. So I don't know if your research is related to photodynamic therapy. Do you know?
Yes.
Okay,
It is.
so one of the applications, one of the photodynamic therapy application deals with energy light energy harvesting by a dye, and then energy transfers. The energy of excited dye is transfers to form the excited oxygen in its singlet configuration, and then excited oxygen is very it's like a radical. It's toxic for malignant cells. So one photo excites this drug, a mix of dye with oxygen in a certain region of tissues, and then only where one initiates this drug by light, it performs killing of the cells. There are some medical terms that I cannot pronounce, like apoptosis.
Apoptosis.
Oh, okay, fine with me.
Okay. Gotcha. Okay. Yes, I think I knew that. Perfect. Also, since you said I can resubmit this to you, correct?
Oh yes, yes. Until
Okay.
until tomorrow 7 a.m. or if it is ready, send it now. Whatever is comfortable.
Gotcha. Do you recommend adding equations for how the figures were created as well?
It is a good practice.
Okay.
And you can. We are not making secrets from each other in the class. You can look what other authors wrote in their papers. Just be alert that there could be errors there, but general idea of how they put equations and then refer to equations while showing figures is a good practice.
Gotcha. Okay. Thank you.
Yeah. Thank you much. Are we done? Okay, disconnecting.